Okay, hi everybody. This is the NASA Big Idea Challenge team's update for this week. This week we've been really busy working on some designs. So our update, current tasks, we designed a test bed to test some of the parameters of the challenge for our prototype. Currently we are done designing our proof of concept and we're going into assembly and building. And we're testing our initial magnetic drive calculations to determine if that's a feasible solution. And we've been working on the microcontroller based systems for the report section.
So our test bed is just a very simple design. It's essentially just a big sandbox, and we're gonna fill it with different materials to replicate the moon as much as possible. We go to the next slide. The dimensions are 4 feet by 4 feet, and the walls are 3 foot by 1 foot.
Here's part of our drive shaft design for this. We are trying to build a very simple eccentric rotation drive shaft, which is very similar to a crankshaft of an engine, just to drive the multi-leg walker as simply as possible, just to test our concept. So here you see our eccentric hub, which has a shaft diameter of 3/4 of an inch, and then an eccentric shaft diameter of 1/4 of an inch to hold our legs. And then our connecting rods are 1/4 of an inch in diameter to hold the shaft again. And the legs, we're just going to use the same dowel, which is another 1/4 of an inch. And then our dimensions there.
To connect the dowel to the motors we're going to be using, we have this motor coupler. It's going to be press fit onto the dowel, and then it's going to match the profile of the shaft on the motor.
So here is some basic math for our magnetic proof of concept. As we mentioned last week, we were thinking about a magnetic drive to separate any of the components so we could seal better. Dust on the moon is a very big problem. So we bought some just very generic neodymium N40 magnets, and we're going to test them at a distance of 0.5 inches, which here we've just found a calculator online to do some quick math to show that we should get a force per each magnet pair of about 0.3 pound force, which hopefully will be enough to propel our prototype through the medium.
For our electronics, we've started making some purchases. We did some rough math and found that the most torque we should need for a motor is 1 Newton meter, and that should be a big overestimate. So we got these 4 FIT 0492A motors. They're 12-volt motors, and their continuous amperage is about 0.7 amps, and their stall amperage is about 2. To control them, we got 4 of those, and to control them, we got 2 H-bridge motor controllers that are controlled by 5-volt logic and can be driven with anywhere from 5 to 35 volts. We got 2 of them. For our applications, the motors should never get to the stall amperage. However, in the future, we may need to buy 2 more, so we have 1 per motor, or put some type of parallel capacitor circuit in if there's a huge spike in amps needed at startup. And then to power it all, we got this 11-volt, 2,700 milliamp hour LiPo battery, and it should be able to run all 4 motors simultaneously at their stall amperages without problems. So, yeah.
All right, so over the next week or so, we have some next steps lined up. We are going to print the currently designed parts on the 3D printer that we need. We have a bunch of files that are ready for that. We're going to actually build the test bed and get it set up in the AIM lab, and then we're going to assemble an initial prototype. So hopefully that'll all be done and ready for the update that'll happen next week. Thank you all for your time, and we look forward to giving you more updates in the future.